This video is about the confidence interval for the odds ratio. So this has been something that interested me for a while. We calculate confidence intervals because we're interested in how accurate our estimates are in terms of representing the true population parameter value. We calculate our confidence intervals around parameter estimates. Parameter estimates are also known as statistics. Statistics are taken from samples, and the idea of doing statistics is to get estimates of population parameters. This is your prototypical equation for a confidence interval. Now, this is the fact that we use z here tells us that this is based on a normally distributed sampling distribution of whatever the parameter estimate is. So we take advantage, of course, of the central limits theorem. The central limits theorem states that we can take some variable that's not normal, and if the distribution if the sample size is large enough, the distribution will converge to normality. The distribution of the sample, right? The sample, like if we take the population sample means from a whole bunch of samples of size n, and we plot the distribution of the sample means for all those possible samples, that sample, the mean of all those sample means will be the population mean. Okay, so we can use this idea of a central limit theorem to convert other variables that are not normally distributed into something that's normally distributed, and then we can use all the beauty of the normal distribution, including all these z values. We know we have these z tables that have every possible probability between any 2 points in the distribution. So we know this distribution really well. Most popular distribution in statistics. So this is your prototypical equation for a confidence interval. You have the estimate plus or minus the margin of error, which is whatever this value, z value is in this case, times the standard error of the estimate. When we deal with the odds ratio, we're using the following equation for the confidence interval. It's the anti-log of the natural log of the odds ratio, plus or minus the same thing, but now it's the standard error of the odds ratio. Here we take a natural log transformation because it actually hastens the convergence of distribution to normality for the odds ratio. That's essentially it. Right? It makes it happen a little quicker. It's more efficient, if you will. The standard error for the odds ratio is this interesting looking equation, the square root of 1. So an odds ratio comes from a contingency table that has 4 possible outcome values. I'll give you an example in a second. So it's a sample size within each of these 4 cells, right? But it is interesting. So we need to know what my interest is. Well, why is this equation the way it is, and why does it look like this? So why is it square root? I mean, don't you see things and say, "What? Why? How did you get that?" If you don't do that, then you're not an academic. Academics look at equations and they ask why, and I'm always asking why. Now, we use the delta method because even if our random variable is normally distributed, some function of that random variable may not have a variance that's normally distributed. We need the variance to be normally distributed as well, because if we calculate test statistics, most test statistics are model divided by some measure of error, like standard error. And if the standard error is skewed in either the positive or the negative direction, it's going to grossly affect our probability of a type 1 or type 2 error, right? Type 1 error means a false positive result. Type 2 error is failing to reject a false null hypothesis. So if you have something that's right skewed, it means there's a lot of larger values. The standard error could, well, if the standard error could be too large, right? And that would result in a type 2 error. So failing to reject a false null hypothesis. That our test statistic would be too small, right? If on the other hand, the standard error is left skewed, there's a lot of small values, we might have overinflated test statistic results, and this would result in a type 1 error, falsely rejecting a true null hypothesis. I'm not going to go into null and alternative. I hope you know what those are by now. If you don't, you should look at a good research methods or statistics textbook. I have a research method statistics textbook if you're interested, and you can read all about those there. So we use the delta method in order to correct our standard error, correct our variance actually, to make sure that we have the appropriate sampling, standard error, right? So we can have more accurate test statistic results. So here is our equation for the this is the delta method, right? So this is square root of n. Well, I'll show you why that's done. Well, yeah, I guess I will. I don't really need to here, but it's a square root of n times some function of, this is our random variable. The reason it's x sub n is that the n tells us that sample size has an impact on it, right? So it's impacted. So as n approaches infinity, this random variable approaches the normal distribution, and the same with this function. This function is going to be affected by the sample size. So that's why we have that sub n. Here I use theta for our location parameter. Could be the mean, could be whatever. So it's some parameter there. So this is just a very general symbol for a parameter. This arrow with a little d on top of it says that it's converging in distribution to a normal random variable with a mean of 0. Now I'll show you how I get that 0 in a second. And this is the standard EV. This is, excuse me, the variance here in this case, not the standard error, the variance. So it's this first derivative of this function at theta squared times the variance itself. So we're adjusting the variance because we're doing this transformation. That's essentially what we're doing here. So we're going to use a Taylor series expansion to arrive at this equation. And I just want you to note that, so this is not, you'll notice that this is not a transform variable, so just x sub n around this, this value theta, and it converges in distribution to a normal distribution of mean of 0 and a sigma squared variance. But again, I'm multiplying by the square root of n, keep that in mind. So let's use a Taylor series expansion. This Taylor series allows us to approximate a function around some parameter using polynomials and derivatives. You know, we can do squaring, cubing, etc. I note that it should be at least twice differentiable. That means you could at least take 2 derivatives of it. I mean, some things you can't because they just become 0 pretty quickly. This is just a very basic looking Taylor series expansion, right? And again, there's lots of literature on how to do Taylor series, but what we want to know is how the function behaves around, like say the mean, a mean of 0. How does it behave around there? So what's going to end up is we can go on to this here. I have k as k being the total number of derivatives I'm going to take of this. But we don't really need to go that far, because what happens is beyond these first 2 terms, these higher order polynomials, while they'll clean in a sense, they'll clean our function and make it a better representation of the actual function, right? Around theta, they really don't add that much more. So what we do is, and this has been interesting to me, because in computer science, there's this little o and big O notation that can be used to deal with these, I guess, these infinitely progressing terms that really, don't do a lot, right? I mean, they help, but they don't do a ton in terms of what we need here. So according to this little O, and again, there's a big O notation as well. So this is some function. You can call this g of x equals O of x sub n divided by x of n. But this term here goes to 0 as n approaches infinity. So in a sense, this denominator bubbles up, balloons, I should say, more so than the numerator. So this approaches 0. So essentially all these terms, we call all these terms, I don't know, we can call it g of x if we want or whatever. All these higher order terms, eventually they become 0. So we can kind of, in a sense, call them error if we like. And we don't really don't need them here to get a good approximation of our function. So let's build this function. So here we have this Taylor series equation 1.7. Here I still have the little O notation, but I got rid of it. This next series of equations. So we subtract this g. So there's a g of theta here. I subtract it from both sides. So this will of course go to 0. So we get g of x minus g of theta. Then you have this first derivative, or g prime theta x minus theta. So this is your prototypical looking term from a Taylor series. You might see something like x minus c or something like that. Just shows how it behaves around some parameter estimate. So we multiply both sides by the square root of n. N to the 1/2 is the same as the square root of n. If you don't know. So this is where we get this really nice looking function, something that we've already seen previously. So using equation 1.5, we go back here, right? We have the square root of n times x of n minus theta converges to normality with n with a mean of 0 and variance of sigma squared. So I'm using what I know there. So I can replace this little puppy right here with a normal distribution with 0 and sigma squared. This is an approximation, right? That's what the double squiggly lines look like. And then if I multiply through, right? So I need to multiply through by this g prime x. And what I get, of course, this is still 0. You multiply by 0, you get 0. When this g prime of theta interacts with this variance term or is incorporated into the variance term, we have to square it because the variance is in square terms. If we take something out of here, we have to take its square root, right? So we get this really nice looking equation, which is our delta method right here. This is the delta method. So this is telling us that now our variances have to be multiplied by this. I don't know why this did that. Darn it! I try to fix it. I have to fix this again, right? Because this is not supposed to be up top here, right? This it should look like this. Actually, let me see if I can fix this real quick while we're here. I do not like having errors like this. I tried my best to fix it before. Let's see. There you go. All right. Cool. As the kid on Community used to say. All right. So just to show the difference, this is just a variance. To be a standard error, I have to divide by n, right? So that's why I had this square root of n out here. I could just divide both sides by square root of n. That gets rid of this. And again, because I'm bringing this into these variance terms, it has to be squared. So it's sigma squared over n. So here we go. We're all set, almost all set, right? Here we have well, let me just talk a little bit about an odds ratio as I move on. Now we're going to use this to calculate our standard error for the odds ratio. An odds ratio is a ratio of odds. Odds are the probability of success divided by the probability of failure. An odds ratio, as I said, is a ratio of odds. So if you have two different levels of something, we'd be comparing level 1 to level 2. This is the odds in each case. So this is a ratio of odds. So let's do this in a contingency table. So we have this contingency table here. And in this case, that we're comparing African Americans to Native Americans in terms of propensity to have a disease. Each of these cells represents a probability. So this is essentially the probability of having disease, probability of not having the disease. So these two are mutually exclusive. So these two would add up to one. Either you have a disease or you don't have a disease, right? If you're African American. So since they're mutually exclusive and those are the only two possible outcomes, I'm not including the empty set or any stuff like that. And the sample space, these are the only two outcomes. They would sum to one. So the odds ratio would be the ratio of these probabilities, right? Remember the probability of success divided by the probability of failure. In this case, we're comparing African Americans to Native Americans, so it'd be success. Now, in terms of statistics, success is getting whatever you're looking for. In this case, but obviously having a disease is not a success from a qualitative perspective. From a statistical perspective, it is. So it's pi 1 divided by pi 1 2, right? And then in this case for Native American, we've got pi 2 1 divided by pi 2 2. I like all the little errors. Yeah, actually, I don't, but that's part of life. So we can also just formulate this equation into a product term, right? If you take a quotient from a denominator and want to bring it into the numerator, we end up just doing this. So we kind of flip it over. So we get pi 1 1 times pi 2 2 divided by pi 1 2 times pi 2 1. A lot of times you'll see these equations for odds ratios with sample sizes rather than with probabilities, but it's irrelevant, because if you take each probability and multiply it by the total sample size, you'll get the n for each cell. So it's just they're different notations. But one thing about odds ratios, they can only be done in 2 by 2 tables. However, here we have a 3 row by 2 columns, so we have a 2 by 3, right? There's 6 cells here, so that you can't really do an odds ratio with 6 cells, but you can work with subsets of that as long as you get a 2 by 2, like we did here. We did African American versus Native American. If we want to use all of these, we may do something like European American versus not European American, and we collapse the cells, but it has to be a 2 by 2 in order to calculate the odds ratio. As I mentioned earlier, we take the natural log to hasten the convergence to normality. When we have the natural log, we can reformulate this, right? This is the same log. Natural log of this quotient is the same as the natural log of the product in the numerator minus the natural log of the product in the denominator. We can fix that even further, right? Because you have this product, so that's can be converted from, say, ln pi 1 1 times ln pi 2 2 to ln pi 1 1 plus ln pi 2 2, and then we subtract the denominator. These are in the denominator, right? So it's minus ln pi 1 2 minus ln pi 2 1. So this is what we will need this in a second, because again, we need to take the derivative of whatever that theta, in this case theta is pi, with respect to each of these terms, right? Just some other notation here. Let's see. So this is actually a multinomial distribution, because there's a bunch of different outcomes here, and any one participant can only have one. Like in this case, there's 6 outcomes. One person can only fit into one of these. One can be African American, have the disease, or African American and not have the disease, etc. So you're in one and not the other. That's a multinomial type of scenario here. But within each cell, for each individual, either you are in that cell or you're not in that cell. So that becomes a Bernoulli trial. So I could say either one is African American and has the disease, or one is not African American and does not have the disease. So that's a Bernoulli trial. Bernoulli trial, there's 2 outcomes, probability, and you really look at success versus failure. So if we're saying we're looking for somebody who's African American and has the disease, being in this cell would be a success and all other cells would be a failure. So that's a Bernoulli trial. And then Bernoulli trial, you have the following: probability of success, probability that this Yij, now I use the terminology I and J. I is the first element here, and the J is the second element. So probability 1 1 would be being in cell 1 and row 1, column 1, right? So this is row 1, column I and J. First item Here's one is in the row and the second is in the column. So that's what I do. Here's the probability of Yij. That means for any one of those cells equals 1 is equal to 1 minus the probability is equal to 0. So this is some stuff you need to know. So this is also saying that if the probability of success is whatever probability y equals 1 is, failure is 1 minus the probability of success. Again, because they're mutually exclusive events with only 2 possible outcomes here. And let's see. Oh, this is interesting too. The probability that y, so you could either be a 1 or a 0, or either you can be a success or a failure. So the probability that y is equal to 1 is pi ij, right? Which is the same as the probability of y ij squared, right? Is equal to, so the probably Yij is the same as the probability of Yij squared, because the values are either 1 or 0. So 1 squared is 1 and 0 squared is 0. So we'll need that a little later. In fact, I'll show you right here. In calculating the variance for each of those cells, we have the variance. This is your prototypical variance equation. I think I have a video showing this as a shortcut variance formula. Give the expected value of whatever the variable is squared minus the expected value of that in brackets squared. But because we know Yij squared is equal to Yij, we can just make this substitution here. And this will come in handy later, because the delta method, we have to end up calculating the variance, and the variance for us is going to be as follows. Sigma squared is equal to, and we're summing across all the cells, all the rows and all the columns, pi ij's. And remember, with the delta method, we had to multiply by the derivative, right? As we saw in the delta method equation, right? We multiplied by the derivative right here, right? Actually, I'm using this one right here at the moment. We have to multiply for the variance. We have to multiply by the derivative right here. So here's the derivative squared. So, well, that's exactly what you see here. You see the derivative squared. So we let phi, some people say phi, some people say phi. I don't know. You go with whatever you want. Phi ij equals this derivative with respect to the particular cell term, right? So we have to do that and square it for each. And we can use the pi ij here because, well, we already saw that the expected value of Yij squared is the same as the expected value of Yij. By the way, this is also can be derived using a matrix equation, using matrices. So this is, you have multiple terms here, and you generally, when you have more than one possible outcome, we use matrices to do that. So you can also derive this equation using matrices. So this is our equation then, right? Now, we're going to use these derivatives. So what I'm going to do is I'm going to walk you through this last part here, and then you'll see how we finally arrive at the answer here. So we take the derivative of pi with respect to each of the cells, right? So the derivative, now, if you recall, based on equation, I think we had 111. Yes, here. The derivative of the natural log of an element is 1 over that element, right? So that's what we have here, 1 over pi 1, 1 for the derivative with respect to cell 1, or because it's row 1, column 1. And for row 1, column 2, we have it being negative, right? Row 1, row 2, column 1, it's also negative. It's because of the terms in that equation that I just showed you. They were either negative or positive, right? So we have these, that's your derivative, right? This first term, you take the derivative and you multiply it by pi ij, right? So basically it's just pi, all these terms are gonna be 1, right? Pi 1, 1 times 1 over pi 1, 1, right? It's 1 minus pi 1, 2, to multiply by 1 over pi 1, 2, that's 1, right? So you get this 1 minus 1, so this is positive, this is negative, 1 minus 1 minus 1, plus 1 squared is equal to 0. So we don't really need, we eliminate that term, right? So we're eliminating that term in its entirety. The next term, we're not doing that because we're only squaring one part of it, but this is pretty easy to solve again, because again, we have pi 1 times 1 over pi 1 squared. So it's basically the same thing. The only difference here, and I don't know how I got this sucker in here. The only difference here is that everything's going to be positive because we're squaring the terms before we do the summation, right? So we get 1 over pi 1, right? Because we can eliminate one of these here, right? Cross one of them out. So we get this. Almost there, right? Almost there. The last thing we have to do is this is our equation of the variance. The last thing we have to do is calculate the standard error. The standard error is the square root of the variance divided by n, right? Because we have to divide by n. You saw that in one of the equations. That's why I actually added the n back in, I think it's 1.13. I added the n back here, right? So you knew that we had to do that to get the standard error. So we got 1 over pi 1 times n, et cetera, et cetera. And these are just going to be the n's for those cells. Taking the square root, we arrive at where I wanted to get. And I'll tell you what, this is so much fun for me to do because I remember walking last summer, hiking. I don't have a lot of time to do this stuff. I'm teaching all semester long. But I remember taking a nice walk, thinking how that, I need to show how this is derived. If anything, it just keeps me sane because I can't stand not knowing stuff, the exact derivation. So I went back and studied that, and you should take that as an example for yourself too. Everything is solvable once you put your mind to it. Thank you very much, and I hope you enjoyed this.